Let's get settled in. So welcome to the second week of our program here. I'm Brian Swingle, one of the organizers. On behalf of all the organizers and the GGI, welcome. We're glad you're here. Just a quick reminder, the current regulations do ask that you wear the mask inside the lecture hall. So if you have one, please wear it. And if you don't, please get one and wear it. We'll also try to do questions via mic. So if you have a question, just raise your hand and we'll come to you. That way the other room and the people online can hear. Okay? And otherwise, without further ado, we're really happy to have Andrea Puhm here today to tell us, this is our first of her lectures, telling us about a primer on celestial holography. So without further ado, take it away.
Thanks, Brian. Is this working? Okay, so welcome everyone, and thank you very much for inviting me. It's an honor to kick off this training week, and as Brian mentioned, I'm gonna give you an outlook of a program that has been developed over the past couple of years, which goes under the name of celestial holography. And what this is that it is an attempt at a holographic principle realized in asymptotically flat space. Now, you may be familiar with the famous ADS-CFT correspondence where holography is at work. So we describe quantum gravity in the bulk of an asymptotic entity spacetime via a quantum field theory that lives at the boundary of this spacetime. And this is a duality, so we can map computations in the bulk of entity space to computations on the boundary. And we can exploit this very powerful duality to gain insight either about difficult questions on the boundary via easier bulk questions or about difficult bulk questions via easier boundary questions. So why would we want to study holography for asymptotic flat space? So let me start with some motivation. Well, the first is an obvious one, which is that we would like to know if there's a holographic principle that applies beyond ADS. Since we have learned so much from holography in entity spacetime, we would like to know if a similarly powerful duality exists in asymptotical flat space, and the obvious motivation for that is that asymptotical flat space is a very good approximation to many processes, or that the spacetime that is asymptotically flat is a very good approximation to spacetimes where physical processes happen in our universe. So for example, if you take the merger of two black holes and you go very, very far away, then fields decay, curvatures are weak, and we are approximately in asymptotically flat space. And so the question is, can we describe these kind of processes in some approximation to our universe via holography? Another obvious motivation is that if it is as powerful as the ADS-CFT correspondence, then it could give us a non-perturbative definition of quantum gravity in asymptotical flat space. There could be alternative ways to get such a non-perturbative definition. For example, if we had a non-perturbative S matrix, then this would already give us a good way of talking about non-perturbative effects in asymptotical flat space. But recasting such the language of a dual theory, which may be a dual conformal field theory, could give us very important insights. Another sort of maybe very big, long haul goal would be to learn about entropy and black hole information. But now for black holes that approximately live in our universe, so for real black holes, by which I mean non-extremal black holes and black holes that are roughly in asymptotical flat space. So these are a couple of motivations for why we would like to study potentially holographic principle in asymptotically flat space. And given that this is such an important question, you might wonder, well, why haven't we done this already? So let me start with some challenges. So the first challenge is that where would we put such a holographically dual theory? So there exists a natural holographic screen. But that natural holographic screen is null. So if I draw the Penrose diagram of Minkowski space, we have a couple of important regions here. So down there we have past time like infinity. Up there we have future time like infinity. So those are the locations where massive particles start and end. Out here we have spatial infinity. That's where spatial geodesics hit. And then these corners here are connected via these null hypersurfaces here that are called past null infinity, or scri minus, and future null infinity, or scri plus. And this boundary, so this is the boundary where we would naturally put some holographically dual theory, so dual to what's happening inside asymptotically flat spacetime. But this boundary is null. And that's unlike ADS, where we would have just a single time-like boundary. Now we have two components of a null boundary, a past component and a future component, and there are these pesky corners at which these boundaries connect. Another challenge is that the boundary in asymptotical flat space is leaky. Namely, radiation can hit the boundary and flux or charge can leave the spacetime. In that sense, it is leaky. And that is also unlike ADS, where we can study quantum gravity in a box. Another challenge is that we have a lot of symmetries here, and that sounds actually like something that we would like because it lets us constrain things. But these symmetries are, well, they're already well known since, let's say, the 60s, but they still have some very puzzling and mysterious features. So what we have in asymptotical flat space is that the finite dimensional Poincaré group gets enhanced to an infinite dimensional group. And this is called the Bondi, Vandenburg, Metzner, Sachs group. So here we have, well, in 4 space-time dimensions, we have 10 Poincaré generators. And then here we have infinitely many. And let me put a beyond here, because there exists also various extensions of the BMS group that has originally been proposed. And then, last but not least, and I'm sure this is not a complete list, but let me finish with the following statement. In asymptotical flat space, we have a rich infrared structure. And that's related to this infinitely many symmetries. So what you might have seen over the last couple of years is that people draw these triangles here, where on one corner they put the symmetries that I just talked about, which are not exact symmetries of the spacetime, but are asymptotic symmetries. And these can also be understood from different perspectives, so can be related to different aspects of the infrared structure of quantum gravity in asymptotical flat space. One is called soft theorems of quantum field theory, scattering amplitudes. So these are some theorems, universal properties of scattering amplitudes or quantum field theory. And then there's another aspect of infrared physics which goes under the name of memory effects. And these 3 different, or a priori different, distinct sounding topics have actually been shown to be intimately related. And this is some special feature of asymptotically flat space. Okay, so maybe let me pause for a moment here and tell you that you should ask questions at any time if something is unclear, or if you want me to elaborate on something. So, yeah.
Is this okay? How important for the whole story is it that we're at infinity? Like, for example, if we're in ADS and we go off to some long distance, but small compared to the radius of curvature, or similar with de Sitter, or we have black holes and stuff that's very far away, do we still have this IR structure and all of that, the infinite symmetries?
Yes. So you could ask, I will talk more about this IR structure and asymptotic symmetries in a moment, but what you do there is first of all, you go to some coordinate frame, so you fix some gauge, and then you ask that your metric, what you call asymptotically flat metric, has some specific fall-offs in the metric components. And if you want to know what the symmetries of the spacetime are, you don't ask for exact killing vectors, but you ask for asymptotic killing vectors that preserve the asymptotic structure that you defined with boundary conditions. And then you can figure out what the symmetries are. Now you could, and these, well, maybe I'm getting ahead of myself now, but so the non-trivial symmetries of the spacetime are those that, first of all, where you have a gauge parameter or a diffeomorphism parameter vector field that does not die off at infinity too fast, such that it doesn't really do anything physical or interesting. But it has some non-vanishing value at the boundary. And then you could imagine taking this boundary inward and asking what would be asymptotic symmetries of some putative hypersurface in the bulk. I mean, you can do that. But at this point, we don't even know really what the putative holographic picture at the boundary at infinity is. So what you're asking would be a question that is beyond that. Yeah. Other questions? So maybe let me just, since I will not talk about black holes, but you could also ask about hypersurfaces in the space-time.
Excuse me?
Yes?
There's a question online.
Please.
It's in the chat.
What is describing this triangle?
Yeah.
Is that a question? Yeah, so this triangle, let me give it a name, which doesn't explain what it is, but just, okay, so this is just saying that there are three corners of infrared aspects of gravitational physics in asymptotical flat space that are not distinct but related to each other. And I will talk more about some of these. So I will talk more about the relation between asymptotic symmetries and between soft theorems. But this is just to motivate that in asymptotical flat space, we have been studying physics in flat space for a long time, many decades. And in the 60s, Bondi, van der Metzner, and Sachs found these asymptotic symmetries. Around the same time, people like Weinberg and many others that are too numerous to mention, have found universal properties of scattering amplitudes in asymptotical flat space, which go under the name of terms. And then around in the 70s, people like Braginski, Thorne, and others have studied what is called memory effects. So these are some when gravitational waves pass through the space-time and pass through some array of detectors, they wiggle and then they go back to some equilibrium position, but it's not the same as before. And this has been called memory effect. And what has been found in the past couple of years is that these three topics, which seem to be very different physics, are actually related, either via change of basis or interpreted vacuum transition, and so on. So this is just to motivate that there's a lot of interesting structure here, and in the course of today and tomorrow, we'll talk more about the corner that I denoted by asymptotic symmetries and the one denoted by soft theorems. So I think this is as much as I will answer this question, since I'm not going to talk about all of these corners in detail. Okay. So now I've told you it's an important question to understand whether holography holds beyond de Sitter space. And I've told you some challenges. So how do we move forward from here? So in asymptotic flat space, the basic observable is the S matrix. And we describe in and out states via the on-shell data, so the on-shell momenta, at the past and future boundary. So let me draw again the Penrose diagram for Minkowski space, but now let me draw two sides. So in this diagram, what I've drawn was a diagram in time and space. Of course, at every point there's a sphere, a d-dimensional sphere in general, but if we go to a four-dimensional asymptotic flat space, it would be a two-dimensional sphere. So every point is a sphere. But here, a pair of points would be denoting a sphere. So a pair of points on the right and a pair of points, one on the right and one on the left, would denote, let's say, the north and the south pole of one and the same sphere. So if I have a scattering process here, some particles coming in, scattering, and then moving out, and I'm drawing here the scattering of massless particles for simplicity. And let's say we do this in general capital D space-time dimension, and let me also denote this by little d plus 2. Then we can compute here the S matrix, so the scattering of in and out states. And so because we are describing this process via on-shell data on the boundaries in the past and on the future, the S matrix already has a holographic character. But we can make this holographic character more manifest. And this is done by the realization that we can recast the S matrix in asymptotical flat space by a correlation function that lives in 2 dimensions less, and it's this sphere that I've told you lives at each point in this diagram and a pair of points in that diagram. And so let's say I have a bunch of incoming particles. They will correspond to insertions of operators on the sphere that lives at the boundary of the spacetime, and then here a bunch of outgoing particles. And we will see that we can write the S matrix as such a correlation function of operators inserted at points on the sphere. I haven't explained to you yet how this works, but this is what we will find. And what this suggests is that quantum gravity in asymptotical flat space, let me say capital D dimensional bulk, so the proposal is that quantum gravity in asymptotic flat space in d bulk time dimensions is given by a theory on the boundary, on the null boundary of the spacetime, namely on this sphere. And this theory I will refer to as celestial conformal field theory, in the hope that perhaps similar to ADS-CFT, we'll find some CFT living on the boundary of asymptotically flat space. And this will be living on this sphere at the null boundary. So this is the proposal. And this proposal goes under the name of celestial holography. Now, one obvious question for anyone familiar with ADS-CFT is this looks like a codimension 2 relation. So capital D-dimensional bulk and then little d-dimensional boundary, which is codimension 2. So where's the other dimension? So we could also ask for a theory that lives on the full null boundary. But theories on null boundaries, they are kind of tricky. Because not only, so what happens is that the induced metric is degenerate. And on these null boundaries, we find a structure that's called Carolian structure. And this would be some ultra-relativistic limit of some field theory. And there's been a lot of work in the past couple of years, maybe decades, on trying to understand such a theory on these null boundaries. What I'm talking about in these lectures is a different approach that's also related. And that different approach says, let me just go to the boundary and look at the sphere that's living at the boundary and use these mathematical equivalents that we can rewrite the S matrix in 4 dimensions or in capital D dimensions as a correlation functions in 2 dimensions or in little d dimensions. So this is just a mathematical statement, and let's try to exploit this statement and see how far we can get. So let me also say here what this relation exploits, and we'll get back to that in a moment. So what this relation exploits is that the Lorentz group in capital D dimensions is isomorphic to the Euclidean conformal group in little d dimensions. And by exploiting these properties, we are allowed to recast the S matrix, which preserves Lorentz symmetry, as something that transforms in a well-defined way under the global conformal group on this sphere at the boundary.
Can this accommodate the scattering of massive particles as well?
Yes. Okay, I've drawn here massless scattering, and actually in view of time, I will only talk about massless scattering, but maybe at the end of tomorrow's lecture, we'll talk about massive scattering, how this can be extended, but it can. It's just that here, so massless scattering is easier to view in this picture because the particles already end up at null infinity, while massive particles end up on these points, start and end on these points here. And so they don't, there's no unique way to associate them with points on the sphere, and we'll have to do something more complicated that involves slicing the space-time into hyperbolic slices, and then using, because three-dimensional hyperbolic space is like ADS3, Euclidean ADS3, and then we can use the bulk-to-boundary propagator in ADS to turn that into a correlation function on the sphere. Because this is more complicated and I only have 2 lectures, I was not going to talk about massive scattering, but you can come and ask me, and I can also point you to some literature. Other questions about this motivational part? Okay. So then let's get to it. So I will start with first introducing some tools in asymptotical flat space. Okay, so let me start drawing again the Penrose diagram. Okay. 0, I minus, I plus, scribe minus, scribe plus, and now I will also, okay. I'm not a good artist, so apologies. So these are constant time slices. And then here we have constant R slices. Out here we have R equals infinity. And there are different ways to go to infinity, to the different infinities. So first of all, a good coordinate to describe the physics near the boundary is a null coordinate here, namely retarded time, so u equals t minus r. And down here, the past boundary advanced time, v equals t plus r. And then if you want to go to future time like infinity, what we do is we take t to infinity at fixed r, and the same at the past boundary, but t to minus infinity and fixed r. If we want to go out to space like infinity, we keep t fixed and take r to infinity. And then if we want to go to these null boundaries, instead of keeping t fixed, we now keep u fixed to go to the future boundary and v fixed to go to the past boundary. Then let's see, at every point here, there's a 2-sphere if we are in 4 dimensions, which I will restrict to from now on. But I can also draw, okay. Oh well. Draw this full diamond, and then we have a pair of points and then one of them will denote, let's say, the north pole, and the other one the south pole of the two-dimensional sphere. And useful coordinates for the purpose of talking about the putative holographic dual at the boundary will be, so that is two-dimensional coordinates, xa, where this a runs over 1 and 2. And as time goes on, we will use complex coordinates on the sphere in order to make contact to two-dimensional conformal field theory. Okay, but for now, let's stick with that. So we have these coordinates r, and then at the future boundary u, or in the past boundary v, and then this coordinates on the sphere. So let me start by reminding you of the metric in flat space, but now in this retarded or advanced coordinates. So a capital X will denote a space-time vector in Cartesian coordinates. And now we want to go to coordinates that are well suited for discussing the physics near these null boundaries. So let's just focus on the future component of the boundary. So this metric is given by minus du squared minus 2 du dr plus then some metric on the two sphere. Let's take the unit metric on the round sphere, gamma AB, dxa, dxb. So this is the metric on this two. And so that's flat space, but we want to let the metric fluctuate. We want to allow for gravity, and it's more generally quantum gravity. So let's do asymptotical flat space. So that will be given by, we want to use coordinates where we can describe the asymptotically flat metric, so the fluctuating metric near the boundary, by the flat metric plus one of our corrections. And good coordinates for this are the so-called Bondi-Sachs coordinates. Let's see at the future boundary, it's u, r, and xa. And so these coordinates, the Bondi-Sachs coordinates, they describe the propagation of gravitational waves that go radially outwards at r to infinity by keeping u fixed. And what this tells us is that the metric, the full metric now, satisfies certain gauge conditions. So it's called Bondi gauge, where we fix the RR component to be 0, the RA, so the angle and the radial component to be 0, and then we also give a condition on the determinant of the metric. So we demand that, so that's called Bondi gauge. And then we can write down the asymptotical flat metric as follows. So we still have the -1 from the flat part, but then we get dot, 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 u squared. Then we still have the du, dr part, but it can also have subleading corrections. Then what was not there in the flat metric is a piece that is with the time, the retarded time and the angles. And then we have the angular piece, which starts with the metric on the round two sphere, plus dot, 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 dxa, dxb. Okay? So we have fixed the gauge, and we have written down how the metric may be corrected at subleading orders. And now, in order to make the statement what I mean by asymptotically flat metric, I have to tell you what boundary conditions I put. I already fixed some gauge, now I have to put some boundary conditions. So writing this out in full glory looks ugly, and we will not actually need all of it, so let me just give you the important pieces here. So the first subleading correction in the retarded time component will tell you about the mass of the space-time, and it goes like 1 over r. Then the time and angle component, there will be a term in there which tells you about angular momentum, which I denote by NA. And then in here, the first subleading term in the angular piece is something that will be important for discussing gravitational waves and radiation. And then there are other components. So for example, actually in here there is a piece that's leading over this angular momentum piece. It's an order 1 piece. But if you impose Einstein's equations, then this subleading component, this CAB metric component here, will actually fix this piece. So this is not independent. And then in here, I demand that the subleading component here starts at order 1 over r squared. So I have specified now how the metric falls off. And I've given this in terms of functions m, NA, and CAB, which depend in general on retarded time u, but also the angles. So this piece here, m, is called the Bondi mass aspect. So this knows about the mass of the spacetime. NA here is called the angular momentum aspect. And this quantity here, CAB, this is called the gravitational shear, or data. And this is a function that can be freely specified. So this is in contrast to these other two, Bondi mass aspect and an angular momentum aspect, which, if you write down Einstein's equations, they have some constraint equations. So their time evolution is constrained, and it's in particular related to this gravitational shear here. This guy is important because from it we can define what's called the News tensor. And this is just given by the retarded time derivative. So the News tensor NAB is given by the retarded time derivative of CAB. And if you square this quantity, then it tells you about the flux, the energy flux. Okay? Yes?
Why do you draw a distinction between NA and CAB? I mean, isn't NA just the flux of angular momentum or flux?
No, sorry. This is NA's one index, and this is NAB.
No, I understand, but aren't they basically on the same footing? NAB is the flux of.
No, this gives you the energy flux.
Yeah, and
so
NA,
they're related via Einstein's equations.
But doesn't NA, what gives you the angular momentum flux then?
Well, okay, so I wasn't going to go into much detail here, but if you write down Einstein's equation, you'll get an equation for dum, which relates it to the data, either the data or its time derivative. And the angular momentum aspect, the time derivative of that is also related to the data and the time derivative of the data. So they're related. So the time evolution of n is related to NAB, but in a complicated way. I was not going to write it down. It's like more than one line on the board.
Yeah, I believe that everything is related to everything by Einstein's equation. That's
yes.
clear. But isn't I mean, I'm just wondering that normally we would say that NA is also on the same footing as NAB, because it likewise carries just as NAB carries the shear is the shear, so how the geodesics ascribe shear, NA should be related to how they twist. Aren't they on the same footing, basically? I don't understand why you call one of them free data and the other
because there's nothing that tells you what this is. This is your input. And from Einstein's equation, you get constraints, and these constraints tell you how the time evolution of these two quantities is related to that free data.
Yeah, okay, well, let's discuss it later.
Okay. So, and let me then just say in words here that now the radiative data at this future boundary is given by the Bondi mass aspect as a function of u and the angles, the angular momentum aspect as a function of u and the angles, and the shear, and they are related via Einstein's equations. And now you can do the same story at the past boundary. And then in order to have a well-defined scattering process where stuff comes in from the past boundary, goes out to the future boundary, you also need to say what happens to these fields, in particular to M and A and CAB near I0, so how these are related. And I will not go into much detail, but this condition for having this well-defined scattering problem goes under the name of antipodal matching condition. And what happens here is that you need to specify fields near this future boundary of scri minus, which I'll denote by scri minus plus, and at the past boundary of scri plus, so I denote it by plus minus, and you need to say how these are identified. And when you say that, let's say, for example, the body mass aspect at scri plus minus matches the one at scri minus plus, this matching incorporates an antipodal identification of the angles. So here these would be antipodal points on the sphere. And what you do essentially is that you demand that your null generator is continuous along these boundaries, and that gives you a condition for how the angular coordinates are matched across these boundaries. Okay? Now, let me talk about the symmetries of the spacetime, in particular the asymptotic symmetries, which is maybe the first thing that we have to figure out in order to see if we have a holographic principle at work, because the symmetries in the spacetime near the boundary have to match those of the theory that we put on the boundary. And this will help us in identifying what this putative boundary theory is. So asymptotic symmetries are important when you have a manifold with a boundary. So let me draw this again. And now, if you do some gauge transformation or some diffeomorphism, which has only support inside the spacetime, then this is, of course, just a redundancy of your theory. But then if you have a diffeomorphism or a large gauge transformation that doesn't vanish at the boundary, then it acts non-trivial on the physical data. So what we do here is we look for the asymptotic symmetry group of this manifold in the spacetime. And this is given by the set of allowed. Let's focus on gravity, so the set of allowed diffeos, modded out by the trivial ones, where the trivial ones are the ones that fall off at the boundary and don't have support there. And these allowed diffeos here are the ones that preserve the specified boundary conditions. So here I've specified that the first subleading component goes like 1 over r, and so on and so forth. And so if any diffeomorphism vector field that preserves that structure will be allowed. And so this will tell us about the symmetries that act non-trivially. On the phase space, or the physical data. Of the theory. And the symmetries that I want to sort of sketch here are the ones that will be most important to us, namely these Bondi, Vanderburg, Metzner, Sachs symmetries. And I will discuss the original ones, which were termed super translations. And also an extension which goes under the name of super rotations. So what you do here is you ask that, so you look for a vector field whose Lie derivative of the metric that I've written down here is not exactly 0, because that would be too much. In flat space we have exact Poincaré symmetry, but here we have asymptotical flat space, so we can only expect symmetries near the boundary. And so you look for diffeomorphism vector fields that, with respect to which the Lie derivative preserves these boundary conditions, but the functions can be different, but it preserves the fall-off in 1 over r. And the diffeomorphism vector field that does that near the future boundary, let's say, includes Poincaré symmetry, so translations and rotations and boost, but it also includes much more. So in particular, so there will be a derivative along the retarded time. So if this is just U, that would just be global time translations. But actually, there can be a whole function worth of such translations. And these functions are are continuous functions on the angles of the sphere at the boundary. So this is the story for extending the usual translations to super translations, where I've restricted here just to what this looks like at the future boundary. And then, so this would be translations, but then the Poincaré group also includes the Lorentz group. And then a natural question is, can you also enhance the Lorentz group? And indeed you can. And the part of the vector field that does that can be written down as follows. And there's a question I come to you in a second. So there is a vector field on the sphere which enhances Lorentz symmetry to some infinite dimensional symmetry. And this here is the covariant derivative on the sphere. Yes?
Does this condition of allowing only these diffeomorphism under the procedure-specific boundary conditions cut out any diffeomorphism you would naively expect to be present?
It cuts out any what?
Does it cut out of the allowed diffeomorphism any diffeomorphism that you would expect to be naturally present in a theory of gravity if you don't impose these boundary conditions? Like, is it a physical condition that we are imposing for some specific reason?
Yeah, so, okay, this is of course a tricky business. What are the good boundary conditions? You would like them to be weak enough so that you can include all of the interesting physics that you could think of, but you would like them also to be strong enough so that you don't have any pathologies. So if it's too strong, then you might just end up with nothing or just a little bit of symmetry, and this will not, you might exclude black hole spacetimes or some other spacetime. So if it's too strong, you exclude too much, and if it's too weak, you might get garbage. So that's a tricky business, and you can give, one can give whole lecture series about good boundary conditions that also depend on what kind of dimension you are in and whether you're an even or odd. There's a whole story here, a Pandora box that I didn't want to open too much. I've put boundary conditions that were proposed in the 60s, and Bondi, van der Boom, Metzen, and Sachs tried to get just the Poincaré group out because far away from any kind of sources, the gravitational field is weak, coverage is weak. You would expect just a symmetry group of special relativity, which is a Poincaré group, but then they tried and they found that you get actually more. And the more that you found is that, forgetting about this vector field here, if you just look at this component, so instead of just getting a 1 here and having global time translations, and then also with some other specific choices here you can get the space translations, they actually found an infinity of functions here. And so the usual translations, which would just be 4 global translations, get infinitely enhanced. And that was the surprise, and for a long time it was contested what it means, and so on and so forth. And then more recently, Barnick and Trossard had picked up that question and asked, well, BMS seems to be there, but what if we, so that enhances translations, but we also have Lorentz transformations in the Poincaré group, so can we also enhance those? What does it give? And that actually then sort of fueled this whole program of, or boosted this whole program of asymptotically flat space holography, because this enhancement of rotations and boosts to super rotations will actually give us something that we want if there was a 2D theory on the boundary, which is local conformal symmetry, and we'll get to that. Thank you. Yes?
So my question is kind of related to the same one, which is there sort of physical, so I'm guessing these super translations, these super rotations, the diffeomorphisms we're considering, and the symmetries, must have some physical interpretation, like a simple physical interpretation from the S matrix side.
Yes, they do.
Oh, okay.
And we'll talk about that tomorrow.
Okay. Thank you.
That's precisely the point. In a sense, well, it relates to what I've drawn here. So BMS super translations and super rotations will be related to certain universal factorization properties of scattering amplitude that include gravitons with very low energy, so taking the energy to 0 or soft. And these universal factorization properties will be related to that. And we will also see that, well, maybe, okay, let me do one more blackboard, and then I'll mention a little bit about that today. So we will see that these symmetries here that preserve the asymptotic structure of the boundary with our specified boundary conditions will have something to do with universal properties of quantum field theory scattering. And now let me just, because I haven't actually told you yet how the BMS arises from Poincaré, extending Poincaré specifically. So we have a semi-direct product of Lorentz transformations and translations in the Poincaré group. I guess I already mentioned that if this function is actually 1, then we get just the global time translations. And you can also pick this function to be certain combinations of the angular coordinates, so that you get also the spatial translations. The Lorentz group arises when this vector field is taken to be a global conformal killing vector field. So that means that the following equation has to be satisfied. dAyb plus dBya is equal to gamma AB dCyc. If this equation is satisfied, then you have just 6 Lorentz transformations, so rotations and boosts. And if you want to go beyond the Lorentz group and enhance Lorentz transformations to super rotations, then you have to give up this equation, at least in the strict sense. You could allow it to be violated at isolated points on the sphere, or you can allow it to be violated everywhere on the sphere, and that gives you 2 different proposals for the asymptotic symmetry group. And we'll talk more about that tomorrow. Okay, then let me, since I'm running short of time, let me just add here that we can compute charges for these symmetries, and that's done via the so-called covariant phase space formalism. That itself would require another lecture. So instead, let me just write down how the charges look like and motivate them. So we can write down charges for super translations at the future boundary. So denote this by a plus, which are given by an integral over the sphere. So usually our charges are integrals of these spheres. There is a determinant of the metric on the sphere. Then there's this function f, which is an arbitrary function of the angles. And then we have m, which is this Bondi mass aspect. And then there's also some kappa squared over, some 8 over kappa squared, where kappa is the square root of 32 pi g. And then, so you see that if f equals 1, so that would be global time translations, then this is just telling you something about the mass of the space-time, or the energy. We can also write down a charge for this super rotation vector field. And that's, again, given by an integral over the sphere. Determinant of the metric on the sphere. And then the vector field YA contracted into the angular momentum aspect. And if this vector field satisfies the global conformal killing equation, then this will tell you something about the rotation, the angular momentum in the spacetime. So these integrals, they go over the sphere on the future boundary. So they are evaluated here near the past of the future boundary. So that's cry plus minus. And similarly here. And we can do the same story and look at what the asymptotic symmetries and the charges are at the past boundary. Denote this by a minus. And this will now be evaluated at the future of the past boundary. And then I've mentioned to you that we have to say something about how the fields behave near these 2 boundaries, how they're related, such that we have a well-defined scattering process. And if we do that, if we say that the Bondi mass aspect, so m at scry plus minus is equal to m at scry minus plus, and similarly for f and ya and na, then we get the statement that the charge at the future boundary is equal to the charge at the past boundary. And that would be a conservation law. which relates back to the symmetries. So this is what we expect. If we have some symmetry, we expect some conservation law. And if you impose this antipodal matching condition between the past of the future boundary and the future of the past boundary, then you get a conservation equation. And then you can ask, is this conservation law satisfied in scattering processes? Is it satisfied by the S matrix? And for this, you plug in this, so you demand that the S matrix commutes with the charge. And then you can check if this is really a symmetry of the S matrix. And since there was a question before, indeed, this conservation law is satisfied by the S matrix, and in fact, it is implied by these universal factorization properties, which are called soft theorems. And we'll talk a bit more about that tomorrow. Okay. Any questions on this asymptotically flat space part? Yes.
So you mentioned the phase space of the theory. Would you think that sort of impulsive waves, like an Eichelberg-Saxel metric or something, should that, in your view, be included? Because if you have metrics that are sort of singular as chi, it's very natural to include also gauge transformations that are singular. Whereas if not, then it's a bit superfluous, really.
Yeah, I would allow Eichelberg-Saxel shock waves and other types of distributional. Girotron, for example, is another distributional.
Well, then that would justify including the Ys, I would think.
Sorry?
I think that would justify why you should also include gauge transformations that have the same singular behavior as chi.
Oh, so I hear, okay, so yeah, good. So originally you might have said, okay, here for this function, this has infinitely many, so it's a continuous function of the angles, but I might want to impose that it's just a smooth function of the angles, and then I can decompose.
No, I meant the Ys, the singular, the general conformal transformation.
Yeah, so you would impose this, and that would give you super translations, and that you're happy with. Now you go to this vector field, and now you say, okay, I want these vector fields to be smooth, I want them to be everywhere well-defined. That lands you on the global conformal killing condition, and then you see that you get only Lorentz transformations. Now you say, okay, let me be a bit courageous and ask, can I include some singular transformations here? And these would be, you might allow singular transformations like we are used to in CFT, where we have things like 1 over z minus w, whose z derivatives is a delta function, right? In 2D. So we might allow such singular vector fields. So if I take a vector field that's given by 1 over z minus w, where z and w are complex coordinates on the 2-sphere. And you might say, okay, I'm happy with that I'm used to in CFT. Then indeed you can actually enhance the Lorentz group. I was going to say more about that tomorrow, but you can enhance the Lorentz group, which is just a global conformal group on the boundary, to the full local conformal group. Then you can say, okay, but let me not just focus on this holomorphic or meromorphic up to a point vector fields. Let me include any kind of vector field. Let me put the z bar minus w bar up there, for example. Let me look at those vector fields. And now this equation is violated everywhere in the sphere. But you could ask, okay, maybe this is an interesting symmetry group, and maybe it's the one in nature. And there are some hints that this might be the good one. But the jury on this is still out there. I don't know if this answered your question. There's lots to be said, and I was... Yeah. Yeah. And then if you allow for such singular transformations, it's natural that you would also allow for singular super translations here. And the question on whether you should do that or not is an open question, active study of research. So I'm not going to say much more on that, probably. Yes?
So about the leakiness of the boundary, these charges are defined essentially like at the boundary of null infinity, right?
Yes.
So what can I think about like the other parts of null infinity? Like if my scattering happens earlier in the retarded time or something like that, like how do I think about those processes? Is there a conserved charge there?
So
like, I'm a little bit confused about how to think about this as a conserved charge along the null boundary, or if that exists at all.
So here I've written down the charge at the past of the future boundary, but you can use now the constraint equation, which is an equation for DUM. to rewrite this sphere integral over an integral over the full null boundary. And then it's just some, then there's a du integral, and then it's just some non-local integral on the whole null boundary. So it's like a, a light ray integral, if you wish.
Okay, thanks.
Andrea, there is also a question on the chat about the relation between kappa and G, whether this is
Sorry,
universal.
I'm in 4 dimensions here.
Okay.
Yeah.
Yeah.
Can you construct representations of the BMS group?
Yes.
Or is it hard?
For what?
Is it hard to construct representations of the BMS group compared to like the conformal group or the Poincare group?
Yeah, so, okay, now we are getting a little ahead. So tomorrow I will tell you, so I already now mentioned that allowing these singular transformations might extends for you the Lorentz group to the local conformal group, which has Virasoro symmetry. So your question was about BMS representations. So the Lorentz symmetry will then act naturally in a 2D CFD as conformal symmetry that we're used to, but the translations will act in a different way, in a sort of unfamiliar way as far as CFDs go, and incorporating how, and I will tell you how that works, and then incorporating that together with Lorentz symmetry, first of all into some Poincare representation is the first step, and then BMS representation is the next. But so far there is not much that I can say about a good way of presenting this, yes. Okay, so now let me go to the next point on this list here, which for the online audience you cannot see. So right now this was an introduction, a flat space primer if you wish, on some aspects of gravity in asymptotical flat space. And then the next 2 parts will be discussing how to recast the S matrix as a celestial correlation function on the sphere at the null boundary of the space-time. That will include what I will call the holographic map, which lets us recast the S matrix in that way. We will then discuss wave functions that we have to stick into amplitudes in order to make the S matrix look like a correlation function, which are called conformal primary wave functions. And I will discuss how to construct boundary operators from them. If there's time, though probably not, I would discuss the analytic structure of these correlators. And then finally, as the last part of this second major part, I will discuss how to extract the operator product expansion from the celestial correlators. And then in the next part, this will be mainly tomorrow, we'll discuss about what I would call celestial symmetries, which starting from Poincare will enhance to BMS, what we have done here already. But now tomorrow we will cover how BMS arises purely from the boundary point of view. And I will discuss how to organize this putative celestial conformal field theory in making use of the representations of the global conformal group. And I'll finish with some open questions on Outlook. And if you want to know more and look at some of the recent papers, I've put up the archive number of a recent review that we wrote with Tristan McLaughlin and Ana Maria Raclario. And there's also lots of references for other lecture notes and other sort of pedagogical works. Okay, so up there I motivated for you that the S matrix, which is defined in terms of the boundary data, has a holographic character, and we would like to make this holographic character manifest and recast the S matrix as a correlation function. And I hinted that this is done by exploiting the fact that the Lorentz group, let's now focus on 4 dimensions, so the Lorentz group in 4 dimensions is isomorphic to the Euclidean conformal group in 2 dimensions. And so I guess I have drawn these pictures up there. So let me just say we want to now recast the S matrix, which we usually write down in a momentum basis. We want to recast the S matrix now in a different basis that makes the conformal properties manifest. I will call this basis the boost basis, since we want to make Lorentz symmetry manifest. And I also said that in view of time, I will not discuss massive scattering, so I'll focus from now on massless particles. Which are given in terms of their, labeled by their null momenta. Let me write this as some sign that tells you about whether the particle is ingoing or outgoing. Then some energy scale, which I will denote by omega. And then some null vector that depends on the angle coordinates. And that null vector I will choose in such a way that it points towards the celestial sphere at the null boundary. And from now on, because it's very useful to do that, instead of using these coordinates xa, which has two components, I will use complex coordinates z and z bar. So this is a point on the sphere. Yeah, this is the energy. This is a sign for in versus out. And in order to set up this holographic map, let me pick a specific parameterization for this null vector. To be specific, let me write it down. It's given by the first component 1 plus c z bar, z plus c bar, I, c bar minus c, 1 minus c z bar. So that embeds the complex z plane into the light cone of R1, 3. And it has convenient properties under Lorentz transformations. So on the one hand here, we have the important labels here are the energy, omega. And we might have particles with spin, so there could also be a helicity, which I'll denote by L. And so this is given by plus or minus the spacetime spin. So we could talk about gravitons, then we have plus or minus 2 helicity. And what the holographic map should do for us, it should replace some of these labels by those that are naturally in a putative holographic boundary theory. So what we would like to find here is that the S matrix recast in this new basis looks like a correlation function of operators O that are inserted at these points Z and Z bar. As I've drawn up there. So this is supposedly how this looks like in celestial conformal field theory, which are abbreviated by CCFT. These operators ideally carry the label under the Lorentz group on the boundary, which is just the global conformal group on the two-sphere. So delta and J are supposed to be those quantum numbers. And then because we have out states, there will also be a sign here, which I'll denote by eta. So this is the thing that we would like to find. And so in here we have these operators, one for in, one for out, and that have these labels. And as you can see, what matches on the left and on the right-hand side is already that they are defined in terms of points on the sphere. And this is nice because we have massless particles that go to the boundary. So we already have these boundary points. But now what we have to do is we have to find a way to obtain these quantum numbers delta and J from the energy and from the helicity. So what we expect here is to find a map that replaces the energy by, let me call it the boost weight, delta. And this is in fact the only thing that we'd have to find a map of, because we can identify the 4-dimensional helicity with the 2-dimensional spin. So these J's will be equal to the L's here. Okay? Okay, so we would like a map from energies to boost weights. And for this, let us look at the asymptotic states that we use in the S matrix, in the usual standard quantum field theory framework, where we use a momentum eigenbasis. So these are just plain waves, e to the I p dot x. which with this parameterization of the massless particle momenta is e to the plus minus I omega q dot x. And we want to map this to some other wave functions that carry definite labels delta and j under the Lorentz transformations that act on the sphere as the conformal transformations. And the map that does that for us is a so-called Melon Transform in the energies. So this is an integral transform. It's similar to the Fourier transform. So we could, for example, take our momentum basis and go to a position basis. Then we do a Fourier transform. Here we want to go from the momentum basis to the boost basis. So we do some other kind of Fourier transform. And that transform is called a Melon transform. And this is the way that the transform looks like. And if you compute this integral of these on-shell plane waves, what you will find is the following. So there's some factors here. There's a gamma function at delta, and then the important piece is this denominator here, minus q dot x to the delta. And I will give this a name. I will call it phi delta. So this is a wave function which depends on a bulk point, and now these boundary points z and z bar through the q's, through these null vectors. And then to be precise, this integral transform only converges if I also give some I epsilon prescription. So I add some regulator, and this means nothing but x mu goes to x mu plus minus I epsilon, and then some time-like vector.
So, sorry, got a question. Sorry.
Yes.
So in your claim that you have like operators, you basically have some sort of like a state operator correspondence.
Sorry, okay.
You have some sort of a like state operator correspondence. Mm-hmm. Is it proven that the map is unique and everything?
Is it true that what?
The map is unique, that each state has indeed a unique
So I
operator.
haven't talked about operator state correspondence yet. I haven't even talked about operators yet. That will come
But you claim that like for each of the matrix elements on the S matrix side, you have a correlator on this side.
Yes.
And then you say that, okay, so each of my particle representation from this side has a definite operator, and you try to map the energies into the boost weights and so on and so forth. Mm-hmm. So this can only be done if you have a unique map.
So, okay. So here, okay, this statement you're happy with.
Yes.
I just take the plane waves, I do this integral transform, I land on something which I will show or not, depending on how far we get, transforms with definite conformal dimension under the Lorentz group. And so that's the statement that is made here. Then in the next step, I will show you how from these wave functions you can construct operators. And that is not unique.
Oh, okay.
In the statement of how you go from wave function to operators, you have to also specify an inner product, and I will get to that. And there's different choices that you can make, and then you get different operators, which are nevertheless, the ones that seem to be interesting for this purpose are related. And I will talk more about those.
But if you try to compute something that is physically relevant on the S matrix side, does the choice of basis matter, or is it?
Okay, so let's say you want to do some scattering process of a bunch of gluons, let's say. And you say, okay, now let me take this proposal for the map, which, let me just write it down, okay. Yeah? So we have done this now for the plane wave. We have mapped it to something. And this something has this dependence on a bulk point and a boundary point. And the check that we have to make is that under SL to C transformations of both the bulk coordinates and the boundary coordinates, this object transforms as conformal primary with dimension delta. If that's the case, then we're happy. We have found something that looks like a natural object in CFD. So I'll get to your question, but let me write down a little bit more. Otherwise, I will not finish. So we have Lorentz transformations of the bulk coordinates, but then we also have how SL2C acts on these boundary coordinates. So in 2 dimensions, so global conformal transformations in 2 dimensions are Möbius transformations. So Z prime is AZ plus B over CZ plus D, where A, B, C, D are complex numbers, and we enforce that AD minus BC is 1. So if you do these two transformations on the coordinate and in the bulk and the coordinate on the boundary, as an exercise, you can show that the transformed object transforms as follows. And in particular, this piece is given by zz plus d to the 2 delta. Okay, so we have, this is, I give as an exercise. It's good to do this. So we have shown here that these objects here that I obtained from Melon transforming plane waves do indeed transform as conformal primaries, in this case scalars, with dimension delta. So this is a 2D, let's say, little d equals 2 conformal primary with conformal dimension delta. And now the proposal is that the holographic map for recasting the whole S matrix as a correlation function is that you do this Melon transform on each of the external particle energies. So Melon each external particle energy. And this way we can define an amplitude. Let me denote it by m. So this is this object. And this I will denote by a, the amplitude in the usual momentum basis. So here an endpoint celestial amplitude. Which will now depend on the external conformal dimensions. It still depends on the bulk points Zi and Z, on the boundary points Zi and Z bar I. And this will be defined as Melon transform of each of those n external particle energies. Of the original momentum space amplitude. And note that this original momentum space amplitude includes the energy momentum conserving delta function. Okay, so that's the proposal, that the map that takes us from the S matrix in the usual standard momentum space spaces to the boost spaces is by acting with the Melon transform on each of the external particles. And now, can you remind me of your question again? You were asking about uniqueness, but there was another question. Or did I answer it? It answered it? Okay, great. Okay. Okay, I'm running a little short on time. So maybe, okay, maybe let me ask you. So I can either now move on and give the general definition of conformal primary wave functions and the operators, and then maybe get to the celestial OPE next time. Yes? Is it what? Are they basis independent? Yeah, well, any physical observer should be independent of the basis, but what you can see so the kind of question that you want to ask about amplitudes might be better suited in one basis versus another. Let me give you one example. If you want to check that this is a translation invariant, the S matrix, this is the good basis because it already uses plane waves which are translation invariant. If you want to check that it transforms as a conformal correlation function, this basis is better. If you want to check here that this satisfies translation symmetry, you will find some unfamiliar looking relation between amplitudes, and we'll talk about that more tomorrow.
But otherwise there is a canonical way of going between the two.
Yeah, so okay, so this goes also into the question of complete basis. So, okay, let me just jump ahead. So here the plane waves form a delta function normalizable complete basis. for momentum space amplitudes. Via this map, you can also obtain a delta function normalizable basis now of these conformal primary wave functions, which are built from these Melon transforms. So this would be scalars, and then for spin 1 and 2 or higher, you would attach the appropriate polarization vectors and tensors. Okay, so let's say complete basis of positive energy plane waves will mean on the boost basis side that you get a complete basis if these conformal dimensions satisfy a certain range or lie in a certain range. Namely, the range is that it has to lie in 1 plus I times some real number. So real part of delta has to be 1, and then the imaginary part can be any real number. And this is called the principal continuous series of the Lorentz group. When you do that, when you restrict your wave functions or operators to lie on this principal continuous series, then you have a complete basis, and then you can map these amplitudes, the original momentum space amplitudes and the celestial amplitudes back and forth. So you can do this transform, but you can also do an inverse transform where you integrate over the deltas instead of the energies. And these deltas will range from, so there will be an integral that goes from 1 minus I infinity to 1 plus I infinity, and then you can recover again from the celestial amplitude, the original momentum space amplitude. Okay? So that's jumping a bit ahead. But it shows you that you can construct complete bases on either side and go back and forth. But actually, what will be most interesting for us in tomorrow's lecture is when we don't restrict to this range of delta on the principal series. But first of all, we can imagine delta being a complex number. And then we will see that when delta takes certain integer values, we'll actually recover these asymptotic symmetries. So that will be for next time. And now, let me just write down for you the definition of conformal primary wave function and operators in general, and then end with that. Okay. Okay, so my definition for a conformal primary wave function, let me denote it by CPW, will be the following. So I will denote a general conformal primary wave function with these labels, delta J, and this is still the 4D space-time in S. So what I demand for that is those are functions on R1, 3 cross C for the ZZ bar coordinates, which depend on a bulk point, a boundary point. They satisfy the spin S, the linearized spin S equations of motion. So for example, for the scalar up there, that would be the massless Klein-Gordon norm. For spin 1, it would be Maxwell. For spin 2, it would be linearized Einstein. And they transform under simultaneous SL2Z transformations of the bulk and boundary coordinates. So that is taking x mu to lambda mu nu x nu, and taking z to AC plus b over CC plus d, with the restrictions on ABCD as above. So under these simultaneous SL2C transformations, we want this wave function to transform as a 2D, and I should say here, satisfy the 4D spin S equation of motion, and it should transform as 2D conformal primaries with conformal dimension delta and spin j. And in general, how does this look like? So the transformation of phi should be as follows. So let me just abbreviate this by a prime. Z prime, Z bar prime. So this is a conformal primary if it transforms in this way. And before I've written just the absolute value since we were looking at scalars, but now I've added spin, so I'll write the z and z bar transformation separately. And this gives me not only the conformal dimension, but also the spin. And then I have the original wave function. And then if this is a vector or a tensor, then I also have to transform the indices appropriately. So let me denote this with d of lambda. So this is the spin S representation of the Lorentz algebra. Okay? So this is the general definition of my conformal primary wave function. And we already discussed the scalar wave function. So scalar wave function was just given by something that looks like 1 over minus q dot x to the delta. And then if you want to go to higher spin, we dress with polarization vectors. So let me denote this here by little phi delta. And then let's say for spin 1, I get a conformal primary vector. Let's say for the one with plus spin, it has a space-time index as well. This will be given by some polarization vector. Let me denote it by mu. And this scalar conformal primary wave function and this polarization vector mu has to be such that this whole thing transforms with definite delta and j. I can also write down the opposite helicity conformal primary vector, which I denote by m bar mu. And then for gravity, which we will also need tomorrow, similarly, now I have indices mu nu, so I will take a product of these two polarization vectors, and similarly for the other helicity. Okay? And now the final part. So we said, in answering a question, I said that if you restrict the conformal dimension of either the scalar or the vector or the metric primary to lie on this so-called principal continuous series of the Lorentz group, so delta is 1 plus I times some real number, then you can obtain a full complete basis. You can do this for the scalars or for the particles with spin as well. And they are the complete basis of conformal primary wave functions. And now the last point that I want to make is define how to get from those 4D wave functions two-dimensional operators. So let me call it a celestial operator. So this will be an operator defined on the celestial sphere. So it will still carry the labels under the global conformal group, but now it only depends on the boundary points. Let me put the spin label here as well. And then depending on whether your particle is incoming or outgoing, there will also be this plus or minus label. And this is now in reply to one of the questions. The way that I define is by using an inner product. So I denote this inner product by these brackets here. And this inner product will be defined on some Cauchy slice that then I will take to the boundary so that I can define an operator at future or past null infinity. What goes in here is a bulk operator, let me call it O hat, that depends only on this bulk point, and is a bulk operator in the Heisenberg picture. And then in this inner product, what shows up here are these conformal primary wave functions that I just defined. And there is a, okay, so now let me explain to you what that means. So how do you usually define an operator at the boundary, like in this momentum space picture? So we want to have a creation and annihilation operators that create for us particles with some definite energy in this picture, and at certain points. Now I want to create operators not with definite energy, but with definite conformal dimensions. So in a momentum basis, what we would do is we would say, okay, let's say for scalars, for example, I would just take this bulk scalar operator, expand it in modes. So D3K, 2K0 for the measure. And then I have some creation and annihilation operators, multiplying the plane wave functions. Okay, k dot x plus a dagger e to the minus ik dot x. For the wave functions, I would put the plane waves, so e to the ip dot x. And then in the inner product, I will use the orthogonality of plane waves, so that in this, when I do this inner product, which for scalars would be the Klein-Gordon inner product, or Klein-Gordon. So if I compute this inner product, the Klein-Gordon inner product, the Klein-Gordon norm of this bulk operator, which go like a creation operator or annihilation operator times the plane waves, together with another plane wave, I use the orthogonality of the plane waves to just pick out A's or A daggers. So the left-hand side would then give me a creation or annihilation operator for a particle of specific energy. Instead of plugging in the plane waves now, I plug in these conformal primary wave functions, and this will define for me an operator that creates a state at the boundary that has definite conformal dimension delta or boost weight delta and spin under the global conformal group at the boundary. Okay, so I think I'm out of time. Let me end with this here and maybe summarize for you what we've done so far. So I gave you some motivation of why holography in asymptotical flat space is interesting. I've explained to you the aspects of asymptotical flat space, some of the challenges that it produces in comparison to anti-de Sitter space. Then we have seen that by exploiting the fact that Lorentz symmetry in the bulk gets mapped to the global conformal symmetry on the boundary, namely on the sphere, we made the proposal that quantum gravity in asymptotical flat space is dual to a celestial conformal field theory. I haven't said what it is yet, but let's call it like that. A celestial conformal field theory on the boundary of the space-time, which is a codimension 2 holography proposal. And then we have looked at different aspects and building blocks of this proposal, notably the map that takes us from plane waves to these new wave functions, which when we stick them into our S matrix elements gives us correlation functions on the sphere. And we have defined what these conformal primary wave functions are for general massless particles, and then ended with defining how you can, from those four-dimensional objects, you can get a two-dimensional boundary operator. And these are the operators that we stick in these correlation functions here, which gives us the S matrix. And with that, I think I'm going to end. Are there any questions?
Other questions?
Thanks. So, okay. These operators have complex conformal weight. Is that bad?
In what way?
I would say if you wanted to construct unitary representations of the conformal group to make conformal field theory, you need real operator weights. So
here we are constructing objects that in unitary representations of the Lorentz group.
Yeah.
Of the Lorentz group, that's what we want. And so from that perspective, they're totally fine. But what you might want to ask is, does this putative celestial CFT at the boundary look like a usual unitary CFT? And I think the answer to that is probably no. But that's not a problem. First of all, we are not in a box as an ADS, so stuff leaks, so maybe you should not expect that. And second of all, the only unitarity that you really want or need is the bulk unitarity. And you can ask, how does that manifest itself on the boundary? But you're not forced to have, anyway, we're on a Euclidean CFT here, you can go to a Lorentzian, but we're not forced to have some unitary Lorentzian evolution here. And in any case, when you go from this Euclidean CFT to a Lorentzian CFT, what you have in the bulk is 2,2 signature, and those are not like amplitudes that satisfy causality or something. So what you really need is the bulk unitarity, and from that perspective, there's no problem with having complex weights. And also in DS, you also have complex weights. So, and we believe that the zeta is important for the real world. So, yeah.
What about this is gravitational? It seems like in all of the S matrix's celestial correlator part, this could as well apply to just a normal local QFT in 4 dimensions, which we know is not a 2D CFT, I'm guessing.
So actually, let's say Yang-Mills theory, that has the nicest properties in this whole proposal, because we'll hopefully see tomorrow, or maybe I just say it in words. So if you look at these amplitudes, in order for, since here you're integrating over all the energies from the d by r to the deep UV, your momentum space amplitude has to have a good enough or soft enough behavior at high energies for this whole integral to be well defined. And in Yang-Mills theory, what happens is that this is because and secretly this comes from the scale invariance of Yang-Mills theory. This is just marginally convergent. But if you look at other momentum space amplitudes, like just tree-level graviton scattering, this will not be convergent. So, but it becomes convergent if you go to string theory, which has a soft UV behavior. So one question here is, if I is demanding that there's a well-defined celestial amplitude, in some sense, an axiom for finding a good UV theory. That could be, I mean, this would be very nice if that was the case, because then we would have one way of checking if a UV theory is a good theory.
I guess what scares me is the claim that Yang-Mills in 3+1 dimensions is holographic, for example, pure Yang-Mills with no gravity?
The claim is that, okay, let me make a specific claim. If you write down n-point Yang-Mills scattering, so let's say scattering of n gluons, let's stick with tree level, then you obtain a correlation function that's well behaved in terms of the energy integrals. So that is a well-defined object in the CFD. And then you can ask questions like, is there an intrinsic 2D CFD that describes everything for Yang-Mills theory? And one thing that I think it does describe is the conformally soft or soft sector of the theory. I think there's good evidence now that there is an intrinsic 2D description of the very soft physics of Yang-Mills theory, presumably also for gravity. But whether this is true for the whole full interacting theory, that's an open question.
Okay, thank you.
So these amplitudes, they often have collinear divergences when you know all this. So especially if you have loops.
This is what I was hoping to get to, but obviously didn't.
Another thing, in gravity you have bound states as well, like or states that are like resonance, like two black holes in sort of in an orbit. How would this manifest itself in this theory?
About bound states, I'm not sure. Yeah, I haven't thought about this question yet, because even there's so many questions before this question becomes one that one can answer. You mean I have, 3 days to figure this out?
Maybe let me suggest, so we can enjoy our break. We're going to have a break now for about 25 minutes until 11:30. And then we'll come back here. And before we go, let's thank Andrea again for a very beautiful lecture.
Just one thing more. So there are 2 coffee machines that we can use with these yellow keys. So if you don't have a yellow key, just look for someone that has